All right, hello everyone. We are going to now learn about the scanning tunneling microscope, the STM. This is the STM. Now the important thing here is the principle is essentially you have a metallic tip and then you have a conducting sample, and somehow you have to get that tip within 10 angstroms, 1 nanometer of the actual sample. And if you get to that close, you could actually have a voltage and a tunneling current of electrons flowing from the sample to the tip or tip to sample. Obviously, if you have that close, 2 items that close, you have to have a very well isolated system from vibrations. This is what the STM looks like. It's got a heavy plate that helps avoid vibrations. It's got little built-in vibration legs on all 4 sides, and that helps keep it from any movement. If you were to tap around it, it won't affect the actual unit itself. The actual electronics for the STM is inside here, and then this guy here is actually the sample holder. The sample actually hooks onto the front, and we just slide it in there. The tip comes out in this direction, and then that's where we let the first a mechanical motor approach to get them very close, and then we use piezoelectronic ceramics to move it literally angstroms at a time so it can get to that close of a distance. The key here was, Binnig and Rohr were the ones, they won a Nobel Prize for this because they figured a whole different method of actually getting to atomic resolution. Okay, these are small, you saw the picture, they're only about 12 inches wide. Now, they realized that if you can actually bring a metal tip within 10 angstroms, 1 nanometer of a sample, that if you put a voltage through it, it would behave like a circuit and electrons would be able to jump from one to the other side through the little gap. But it has to be very close for that to happen. And then they were wondering, well, how do you keep the tip from actually crashing into the sample if it's literally only 1 nanometer away? Well, there's a feedback loop in there that's going to monitor that current, how many electrons are flowing per second, and if that value goes up, it's going to realize it's gotten too close. It's going to mechanically, or with the piezoelectronics, move the tip away. If the current drops and gets below that set point, it's going to realize that it's further from the sample than it should be. It's going to move the tip towards the actual sample closer. And they also realized that if you could actually get a piece of metal, cut it at an angle and shear it, you can actually get it so it pulls 1 electron, 1 atom, sticks out further in the metal than all the rest of the actual metal. And that will be the actual probe we're going to use to run the apparatus. Now here's the shown here. If my tip and my sample are more than 10 angstroms, 1 nanometer apart, there's going to be absolutely no voltage. They're going to be too far apart and we'll get nothing. But if we can actually get them close enough where we're actually just a little bit less than 1 nanometer, then we can actually have a current where electrons flow from the tip to sample or the other way around, and we can actually measure that amount. And you can see also that as it gets closer, it goes up a lot, which makes it a lot easier for the feedback loop to adjust and get it back to a constant height. Here. And then this is part of the scanning probe microscopes, all right? The STM we're dealing with, that'll be one. There's also another famous one called the AFM, the atomic force microscope. That works with a little stylus cantilever, and it has a little teeny tip, and it basically uses repulsive forces and traces samples. And we can also get a lot of information from that. Now, the scanning tunneling microscope, the only downfall is it has to be a conducting surface, because if you had a plastic, for instance, you're not going to have electrons jumping to or from the plastic. Okay, here's shown here visually what we're saying. If I have a voltage going on here and I've got these electrons acting as waves, we know that in classical it says when it reaches the end, it would go to 0. Likewise, any electrons that are excited on the sample, once it reaches the end of the sample, goes to 0. But the reality is it drops quickly, but it does not just go to 0, boom. There is a decay. Okay? Now, if we can actually get these guys close enough, again, 1 nanometer or closer, suddenly these will start to intersect, and they're going to have a measurable actual potential, a voltage, and we'll better measure the current of the electrons flowing. Now, if I have no voltage going through these tip and samples, well, naturally, nothing's going to happen. We can't get electrons to jump without giving them a little help of voltage. Now, my bias voltage, if I have a positive What that'll mean is I'm going to have my voltage going from the sample to the actual tip. What happens there is, as I'm putting the volts in here, it raises the electron energy levels, and we can actually now have electrons jump this gap to go to our tip, and we can measure that. If it's a negative bias voltage, it's just the other way around. Now we're putting the voltage into the tip, and it's going to end up jumping the electrons to the sample. Okay, now, about the microscope itself. The human eye can see down to about 100 microns, about 0.1 millimeters. That is essentially like the thickness of a thin hair. So that's pretty good. Now, the basic optical microscopes that you see in like biology labs, most of those are probably around 60, maybe 100 power, but you can go upwards to around 1,000 power, okay? Which means that now, with those, we can go all the way down to 0.1 microns, pretty small. But there are limitations, because obviously we're using our eyes, we're using the visible spectrum. And 400 to 700 nanometers is going to limit how much we can zoom really in accurately. Now, as far as electron microscopes, well, they actually use X-rays, and we know that X-rays are high energy. They are very, very short wavelengths, and because the wavelengths are shorter, we can actually go down, get more resolution. And that one's about 0.01 microns maximum. Put the shade on here. That's about what I think it is. We also have the scanning electron microscopes, SEMs. They're large, they're very expensive, but they work to around also about 0.01 microns. And again, 0.01 microns, that's 10 nanometers, right? Which is 100 angstroms, not quite atomic scale there. And then the acoustic microscopes. Well, we know them mostly for like MRIs, if you have an injury, also ultrasounds for pregnancy and things like that. They use a coupling fluid, but they can still get down to about 0.2 microns. But the important thing here is that because they're using sound waves, that they can actually penetrate through the body and see internal organs, see inside, things that you don't see directly. So that can see things below the surface of skin and so forth. Now, here's showing a basic sample and the tip. Now again, the tip, we're going to set it up. We set a particular current. So we want to have, like, say, I want 1 nanoamp current to flow as my tunneling current. That's going to determine how close it gets. Obviously, if it gets closer, it's going to be more than 1 nanoamp. If it gets further, it's going to be less than 1 nanoamp. Now, there's two ways we can do this. One way, which isn't used very often, is what they call constant height. And all that does is the tip doesn't move forward or back toward the sample. So it stays at one place, and what it does there is it's going to read current. It's going to see a small current, a big current, smaller current, big current, and then it takes all those data and we get an image. The problem there is if I have anything that sticks up a little higher than where the tip is, naturally the tip's going to wipe it out, and it's going to probably damage our tip. We'll have to have a new one made. The most common is we use constant current mode. What that does is it tries to maintain the same exact current during the entire scan, which means it's trying to stay the exact same distance away from the sample. Okay, now here, electronic feedback I mentioned. What happens now? What happens if it senses a decrease in current? Well, if it's right here, and it goes down to this area here, notice the distance is now greater. That means there's going to be less electrons that can jump that gap. The current will drop. It's going to realize the current went down. It's going to move the sample and tip closer together. So now the tip will move down. If otherwise here, if it gets to this point, now it's getting very close to the sample. The current's going to go up from the 1.0 set point. It's going to realize that, oh, it's bigger than 1. I need to move the tip away until I get back to 1.0 nanoamps. That's our set point. So what happens at the end is, if it keeps the same distance away, you can see that the trace and outline is exactly the same as the actual sample surface. And we can actually then get our topographic map. Now, how do you actually move a tip, literally angstroms at a time? Well, they use what they call piezoelectronic ceramics, PZTs. This diagram shows here that in this particular apparatus, these STMs, it's got 3 of these, one going in the X, one Y, and one in the Z. Okay? So that way it can move in any direction it wants to. Now, naturally, the X and Y movements, they're just to do what they call a raster scan. It's just going to move this direction, move down another row, get another one, move down another row. So those will be used to actually maneuver to do the scan. And of course, the Z piezoelectronic ceramic is going to be used to actually move the tip closer or further. Essentially what they do is when you put a volts in one of these, you can actually change its shape. You can actually make it lengthen, make it thinner, or contract and get bigger, wider, okay? And that's how it moves back. So if I want to move this guy closer, you'll just simply put a voltage that'll cause this guy to thin out a little bit, but become a little bit elongated. It'll push the tip closer. Now here's some diagrams of the apparatus. Again, this is the actual front of the STM here. This is the back view. And you can see, it's just got a power connector. We've got a USB connector that connects to the computer. And then when you power it up with the power button, the little blue light will light up here indicating it's powered on. And then when you get the software running, it'll connect to it and we'll be able to actually operate. This shows here where the sample goes. That is the actual tip that we're going to be using to do the measurements. And we've got a magnet here, and then we've got basically a slide or sample that's going to be looking like one of these. We're just going to slide it in, put it past these approach motors, and get it as close as we can safely without hitting the actual tip. And then once we have it set, we're going to put a cap on it. And the cap is going to basically also have a magnifier on it. So it makes it a lot bigger. And then we can actually use mechanical motors to get it very close. And then we'll then use those piece electronics to move it really, really slowly, safely towards the actual sample until it reaches about 1 nanometer away from the actual sample itself. Now here's showing here how to get the wire cut. When you're cutting it, you're holding with these tweezers. You've got the wire sticking up. Again, you can see here, we're cutting it at an angle because you don't want to just cut it flat. We want to have one tip stick out where one piece sticks out further than the rest. And then what we do is, before you actually just cut it, you're actually pulling this arm down, this arm up. And then when you cut it, you're trying to stress it so it kind of bends that metal, and we have one little piece that's sticking out higher, further than the rest. That's what we need to have a good probe. And then we take that, and we basically, this is where the holder is. We just basically put it in here, slide it this way until it goes into this little channel, and then we're good. And then we can actually then run it, it'll be stable. And then again, this is where the PZTs are located to move that around and back and forth. All right, important things here is that you never ever want to touch the actual samples with your finger because you're going to have some oils on your finger. Oils are not very good conducting as often. So you want to keep the samples as clean as possible. You want to use tweezers when you're actually taking them and actually putting the sample holder onto the actual, this guy, the big cylinder holder. That's a magnet right there. When you get it close to it, it'll pull right to it. Once you have it on there, you can use the tweezers and sideways to center it how you want, and we're good to go. And then we're going to load it from the right, slide it really close, and then you'll see here that once we get close, we're going to use this advance button. The advance moves the mechanical motors, and it moves it fairly quickly. Then if you look through the little magnifier, we're going to see the actual STM tip, and we're going to see the sample moving closer. And off the sample, it is a conductor. We'll actually be able to see the actual reflection of the tip. And we're going to use the advance to get it as close as we can so it looks like they're practically touching one another. It needs to be close because the piezo electronics move angstroms at a time. If I'm I'm a millimeter away, it'll take it forever to get that point. So we're going to get it really, really close. All right, here's a picture of the software. Obviously, we have to program so we know how large the area do I want to actually scan, the image size, how quickly I want to run my scan, how many data points do I want. All the parameters are going to go right up here. The Z controller is my set point. In this case, I want to have it so the tip and sample are so close that it'll actually allow 1 nanoamp of electrons to flow. And then the P gain, that's proportional gain, and integration gain, those are part of the feedback loop. Again, that's where if I'm scanning and I've got a tall feature and it goes from 1 nanoamp to 2, that's going to affect how quickly it corrects itself to go back to 1.0 nanoamps. All of these values are going to go in this part of the software. And the last thing is the tip voltage. In this case, we've got a positive 50 millivolts. A positive bias means that the electrons are going from the sample to the tip. Okay? Then we have the 2 windows here. This window and this window are going to look pretty similar. What this guy really is, this is the one we actually want to use. This is our service, okay, that we actually get from the STM. This is actually what creates it. These are going to be all currents, and it's going to let you know if the current is high or low. Naturally, if the current is high, that means we have a tall part of the feature. If the currents are low, which would be a light color in this case, it must be a low, like a valley feature. But this is going to be the actual one that's going to give us our final image, okay? And then way over here, if you click on gallery, it shows all your trials that you've run in the past and so forth. Here, this is part of the acquisition. Obviously, this is how we're going to acquire our images. There also is an analysis that allows us to do cross sections. We're going to just draw a line across. And when you draw a line across it for a cross section, it's just like you take a knife, cut it up, and then you're looking at what you have. And that's very important because you get lots of numerical data based on, what's the distance from here to here, for instance? What's the distance from this guy to this guy? You can get a lot of numerical data down all the way to, theoretically, the atomic scale. Now, the samples we have, the one sample, kind of the neatest one, is the Hopg. That stands for highly oriented pyrolytic graphite. Okay? When you first scan it, we're going, I think, 200 nanometers by 200 nanometers. It's going to look just like a bunch of dots, kind of, orange ones for tall features, blacker ones for the lower features. And then we're going to zoom in on it, run another scan, zoom in again and again, and when we get the last fourth one, we're going to actually already be down to 2 nanometers by 2 nanometers, which again is only 20 angstroms. And you can actually get that close when it's working properly. And you can actually see here, here's the structure of graphene. It's just carbon, right, in this kind of pattern. And then the next layer down is offset a little bit, and then it goes back and forth. We can actually we can see the atoms right there. We can get the distance between here and here. We can get the distance between this row and this row, and that row and that row. As much numerical data as you can to make these kind of measurements, okay? Now, another sample we have is this piece of copper. You look at the copper metal, it looks really, really smooth. But we're going to use this STM to show you that, indeed, atomically, they're not smooth at all. So again, we're going to get a scan. In this case, you can actually see little stress points. Looks like something had a little cavity right there. Again, we don't need to zoom in on this guy, but if we do a cross section, we're going to see more than likely that the high and low distances are not like 5 nanoamps, they're probably 100 nanoamps or more than that. It's much more ragged than the graphene by far. Another one we have is what we call it. It's basically a gold that was deposited onto a wafer, and it's a 1-1-1 orientation. And what happens on that one is it's super smooth, but it looks really bumpy here. But what we find out is that you can see the little plateau. It goes from here, it drops down, and then drops down. Each of those drop downs are only 1 atom. And we're going to measure that. We're going to see that, that's only about a 0.3 or so nanometer difference between this height and this height. And likewise, this guy and this guy. So it's like a step going up and down. Yeah, it looks bumpy, but it really turns out that even this peak compared to that are only like a couple nanoamps or nanometers away. And that's all I have for you. I wish you could be here and actually run the experiment. It's a really neat machine, and when we finally get back, I would be more than glad to set one up and have you guys come in and try them out if you'd like to see what they're like. All right, well again, this is Paul. Thank you very much.